Good day wherever you are. I want to take you through chemistry practical paper 3, that is of the year 2018. As you can see, it was November 2018 when the paper was done. So please let us just go in to the next page so that we can look at the question. You are provided with 0.3 grams solid A, magnesium metal, hydrochloric acid, solution B, 0.5. There was a mistake. 0.5, and it is supposed to be 0.15 capital M molar. 0.5 molar sodium carbonate, solution C, and then methyl orange indicator. What are you supposed to do? You are required to determine the enthalpy change per mole of the reaction between magnesium metal and excess hydrochloric acid, and then calculate concentration in moles per liter of hydrochloric acid, solution B. One thing you need to know from here is that the solution B that was used was 50, but now we are not going to do this procedure 1. We want to go to titration first. So let us go direct to titration, and then we shall see. This is our titration paper. So let us read the procedure. Fill a clean burette with the 0.15 molar sodium carbonate, solution C. Place all of the mixture in the beaker from procedure 1 into a 250 ml volumetric flask. Add distilled water to the mark and shake thoroughly. Label the mixture as solution D. Using a pipette filler, pipette 25 cm³ of solution D into a 250 conical flask and add 2 drops of methyl orange. Titrate solution D in the conical flask with sodium carbonate, solution C, and record the table from the table 2 here below. I want to, because we have not done from procedure 2, but I want to remind you that in procedure 1, what happened is that 50 cm³ of solution B was used, and solution B is hydrochloric acid, but this hydrochloric acid was in excess. It was in excess, so a certain number of moles reacted with the magnesium carbonate, and some acid remained. The acid, because it was in excess, acid remained. Now we are taking HCl from the first procedure to dilute it more in procedure 2. So you should have that in mind, that from procedure 1 we will take 50 cm³ of solution B, which is hydrochloric acid, Thank you. Now we have diluted the 50 cm³ solution B after reacting with the metal, and now we have added we have put the solution into the conical volumetric flask, and now we have made it into 250. This is solution B, which we have added water to up to 250 ml in the volumetric flask. We have prepared a solution we call solution D. Now we are titrating solution D, but remember solution D is hydrochloric acid. Hydrochloric acid is solution D is HCl. The difference between B and D is the concentration and the number of moles which has been, because this one has been diluted. So let us use this in our table. let us use 23.5, 23.5, 23.5, our initial 0.0, 0.0, 0.0. Our arithmetic here is 23.8, 23.5, 23.5. So let us go ahead and calculate the average, determine the average of the carbonate. Remember, so the carbonate volume of solution, what is here? Now look at this. Fill a clean period with the carbonate, solution D. So you see, we are supposed to have volume of solution C. No. Yeah. Here, this is another mistake, this paper head. This one is supposed to be volume of solution C. Volume of solution C used. Yeah, this is the mistake, this paper head in 2018. They had a lot of errors. So determine the average volume of solution C that was used. So we have used, that is 23.8 plus 23.5 plus 23.5 divided by 3, which will give us 23.6 centimeters cube. Next page. Calculate the number of moles of sodium carbonate used. Calculate the number of moles of sodium carbonate used. Number of moles of sodium carbonate used. Remember, we were given that 0.15 capital M. This is the number of moles of sodium carbonate in 1 liter. This implies that 0.15 is the number of moles of sodium carbonate in 1,000 centimeters cube. So we have used 23.6 centimeters cube of solution C. We will ask 23.6 will give us how many number of moles. That's what we want to calculate. 23.6 times 0.15 divided by 1,000. This one will give us 0.00354 moles. Calculated the number of moles of hydrochloric acid in 25 centimeters cube of solution D. So remember, this is HCl, solution D reacting with sodium carbonate, which is going to form sodium chloride plus CO2 plus water. The ratio here we put 2 here and then put 2 here. So the ratio of the acid to the carbonate, or the ratio, mole ratio, that is the carbonate, sodium carbonate to HCl, the ratio is 2 to 1. But we have the number of moles of the carbonate from Roman 1. The number of the carbonate that reacted with HCl, solution D, is this one. This is the number of moles. So it means that the number of moles, moles of 25 centimeters cube, solution D equal to 2 times 0.00354, which will give us 0.00708 moles. That is the number of moles of HCl that reacted with the carbonate, because 25 was pipetted from solution D. Calculated the number of moles of hydrochloric acid in 250 centimeters cube of solution D. So now we have the number of moles in 25. So we will ask, what about in 250? 25 centimeters cube. Solution D has 0.00708 moles. 250 centimeters cube. Solution D will contain how many moles? 250 times 0.00708 divided by 25. This one will give you 0.07. You move one decimal place, 0.08 moles. Calculate the number of moles of hydrochloric acid that reacted with magnesium metal. Okay, magnesium reacted with HCl, solution B now. Remember, this is the number of moles of solution B because solution B reacted with magnesium to form magnesium chloride plus hydrogen gas. But remember, we were given from here, we were given that 0.3 grams of solid A. So magnesium, it requires 0.3 grams. We have been given the RFM of magnesium, the RFM or RAM. So moles of magnesium is equal to mass of RAM, which is equal to 0.3 divided by 24. Gives us 0.0125 moles. So the moles of HCl, so we must balance this too. We must balance this. It's balanced. So moles of magnesium is 0.012. If moles of magnesium is 0.01 and the ratio is 1 to 2, what is the number of moles of HCl? The ratio is 1 to 2. Therefore, moles of HCl is equal to 2 times 0.0125, which is equal to 0.025 moles. So this is the number of moles of HCl that reacted with magnesium. Calculate the number of moles of total number of moles of hydrochloric acid in 50 centimeters cube solution B. So we want to calculate the total number of moles. Now here there is a number of moles that reacted with solution B that reacted with magnesium. We already have them. So 0.025 moles reacted with magnesium. Another portion here, this one, we have prepared 250 solution which contains this number of moles. But solution D, 250 solution B, what was that? That is the HCl that remained. So the number of moles in 250 we add here. So you add number of moles in 250. So which is 0.0708, which will give you a total of 0.0958 moles. Determine the concentration of hydrochloric acid in moles per liter of solution B. Now we have the number of moles of 50. Remember initially the total volume of solution B that was used was 50 centimeters cube, which is now 0.0958 moles from our previous calculation. We ask what will 1,000 centimeters cube of solution B contain. This one, when you multiply, use your calculator please, it will give you 1.9 0.16 moles per liter. You can use capital M to represent moles per liter. Now let us go to question 2 and look at the qualitative analysis part of it. You are provided with solid E. Carry out the following test and record the observations and inferences in the spaces provided. Place about 1/3 of solid E in a dry test tube. Heat the solid strongly and test any gas with both blue and red litmus paper. Test any gas with both blue and red litmus paper. So the observation is there. When you heat a solid, you expect the following observation. So this was the observation made. Colorless liquid condenses on the cooler parts, condenses on the cooler parts of the test tube. So if a colorless liquid condenses on the cooler parts of the test tube, it confirms that there is an hydrated salt. There is a salt which contains water of crystallization. So you can also say water of crystallization. That salt contains water of crystallization. What happened to the red and the blue litmus paper? Red litmus changes to blue, and then blue litmus remains blue. So if red litmus paper changes to blue and then blue litmus paper remains blue, that confirms that the gas that was produced is a basic gas. So there you write that ammonium ion is present. Remember, ammonia is the only gas that is basic, so we use ammonium ion present to imply that the gas that was produced is a base. Place the remaining amount of solid E in a boiling test tube. Add about 15 centimeters cube of distilled water and shake. Divide the mixture into 4 test tubes. Each containing about 2 centimeters cube of the solution. Now to the first portion, add 3 or 4 drops of dilute hydrochloric acid. Always when you are adding dilute hydrochloric acid, you expect a white precipitate of lead chloride. If there is lead inside, it will form a white precipitate. If there is silver, it will form silver chloride, which is a white precipitate. Those are the things we expect. Also, when we are adding an acid into a salt, we don't know, because it is an acid, we expect effervescence. That's another thing we expect when you add a salt, an acid into a salt. If it is a carbonate, for example, it will produce effervescence. So you would also expect an effervescence. So the observation is that number 1, there is no effervescence. No effervescence. If there is no effervescence, then it means if inside there was no carbonate, there was no sulfite, there was no hydrogen carbonate. Absent. This was absent. Another observation is that there is no white PPT. No white no white PPT formed. If there is no white PPT formed, then it means that inside there were no lead. We expect a white precipitate with lead chloride, or silver. Silver is positive 1. Silver were absent. These two ions were absent because they form a white precipitate with a chloride ion, so they were absent. To the second portion, add 2 or 3 drops of aqueous barium, so barium nitrate. And then the observation is that barium nitrate, a white precipitate is formed. White precipitate formed. White PPT formed. So a white precipitate has been formed. Barium sulfate, we expect the following. We expect the carbonate, the sulfite, and then the sulfate. But since from our previous Roman 1, we have said that there is no carbonate, there is no sulfite. Therefore, what is there? It is the sulfate which is there. Don't just say that this one present yet. In our previous inference here, we have said that this sulfite, carbonate, and are not there, absent, because of this no effervescence. And now, when you go to the next one, you will contradict yourself if you say that the carbonate and the sulfite is present. Therefore, the only anion you are going to write is that the sulfate is present. It is the sulfate which is present. To the third portion, add aqueous sodium hydroxide dropwise until in excess. So here a white PPT is formed. White PPT formed, which dissolve in excess. Sodium hydroxide. A white precipitate is formed which dissolve in excess. So there we expect the ZAP ions, the zinc, aluminium, and the lead. So we are supposed to write all of them: aluminium, zinc, and lead. But in our previous inference in Roman 1, we have said here that lead is absent. So if you put it here that it is present, then you contradict yourself and you are likely to lose a mark. Therefore, we leave lead out, and then we infer that aluminium 3 positive and zinc 2 positive is present. We leave it out intentionally because in our previous we have said that it is not there. Thank you. Now, man 4. To the fourth portion, add aqueous ammonia dropwise until in excess. Aqueous ammonia simply means sodium, ammonium hydroxide. Then a white precipitate, white PPT, which does not dissolve in excess, that is insoluble in excess ammonia solution. A white precipitate is formed which does not dissolve in excess ammonia solution. Now that confirms that aluminium is present. Or another thing that this one is telling us, it is telling us that the zinc 2 ions is absent. Remember, if the zinc 2 ions were absent, the white precipitate formed will dissolve to form a colorless solution, which is going to form the complex of the zinc. It's called zinc tetraamine zinc 2 ions. Tetraamine zinc 2 ions, the complex salt. Let us go to the other, number 3. You are provided with solid F. Carry out the following tests and record the observations and inferences in the spaces provided. Place about 1/3 of the solid F on a clean metallic spatula and pan it in a Bunsen burner. So when it was burned, what happened? So the solid F burns with a yellow. Solid F burns with a yellow. Burns with a yellow sooty flame. The solid F burns with a yellow sooty flame. A soot means smoky, the one that produces a lot of smoke. So what is the inference? This means that the unsaturated organic compound is there. So you can use the words that unsaturated organic compound present. The unsaturated, we know we have 2 of them, that is the triple bond and the double bond. So you can also the alkene and the alkyne. Therefore you can say, if you can't remember this one, unsaturated organic compound, just write the functional groups of the alkane, alkene and the alkyne. So you write this one. If you forget this, write the double bond and make sure each carbon is surrounded with 4 covalent bonds, or the triple bond. Make sure each carbon is surrounded with 4 covalent bonds, and then you say present. Yes, present. Place the remaining amount of solid F in a pouring tube. Add about 10 centimeters of distilled water and shake. Use the mixture for test Roman 1 to Roman 3. So solid F dissolves, forming a colorless solution. Solid F dissolves, forming a colorless solution. That means that whatever solid the solid is a polar organic compound. Polar organic compound. A polar organic compound is a compound which dissolves in water. The one which does not dissolve is called non-polar. Using about 2 centimeters cube of a mixture in a test tube, determine the pH using universal indicator, paper, and chart. So here you add the around about 2 centimeters of the solution in, and then mix it with an universal indicator, 2 centimeters equal amount, and then check the color against the pH chart. If the color is red, then the pH is 1. If the color is green, yellow means a pH of 6, which is a very weak acid. Green, pH of 7, which is a neutral, something like that. For this one, the pH was 2. So if the pH is 2, it simply means that the solid was an acid, so strongly acidic. To about 2 centimeters of the mixture in a test tube, add 2 or 3 drops of acidified potassium manganate. Here, so the purple potassium or acidified potassium permanganate, purple acidified potassium permanganate, there is in here, is decolorized. Manganate 7 is or changes to colorless. Purple acidified potassium permanganate 7 changes to colorless. It simply tells us that there is a double bond unsaturated. There is a triple bond. There is also an alcohol. But since we have said that what was inside was remember, alcohols are saturated. ROH, these are saturated organic compound because they burn with a blue non-sooty. So if we put ROH here, we contradict ourselves. Therefore, we cannot put it here, because already we said what is present is an unsaturated organic compound. So if we put R here present, we contradict ourselves. Although the acidified potassium permanganate is used or is decolorized by ROH alcohols. But in this case, you are not going to put it here. Why? In our previous inference, we have said that what was present is unsaturated organic compound, alkenes and alkynes. Therefore, we cannot put it there. So we say this one present. To about this mixture, add 2 or 3 drops of bromine water. And bromine water is decolorized. And that also says that the triple bond or the double bond is present. Thank you. Subscribe. You can call. We have our contact there. If you have any question, you can ask. We are always free. Thank you and be blessed.